And the table here shows how you calculate the standard deviation. So next we have ways of visually presenting the data that you can receive. The first way is using a line graph. A line graph is commonly used to display change over time as a series of data points connected by straight line segments on two axes. The line graph therefore helps to determine the relationship between two sets of values, with one data set always being dependent on the other set. Line graphs are useful in that they show data variables and trends very clearly and can help to make predictions about the results of the data not yet recorded. For example, my line graph shows the relationship between pre-static and post-static sprints in different individuals. My graph shows that all the individuals had a quicker time in their post-static sprint. Next is bar charts. Bar charts are often primarily used for displaying the quantities of qualitative or categorical data, e.g. an age group, although they can also be used for quantitative data if the number of unique scores in the dataset is not large. A bar chart plots the number of times a particular value or category occurs in the dataset, with the length of the bar chart representing the number of observations with that score or in that category. Bar charts can be displayed horizontally or vertically, which are sometimes referred to as column charts, and they are drawn with a gap between the bars. For example, my bar chart is vertical and shows the relationship between the systolic and diastolic pressure of different individuals. Next is scatter graphs. A scatter plot or scatter graph is used to display the relationship between two quantitative variables plotted along the axes. A series of dots represent the position of observations from the dataset. The independent variable is generally plotted along the horizontal x-axis, and the dependent variable or the responsive variable is plotted along the vertical y-axis. Usually scatter plots have a single line called a regression line running through them. The line of the scatter plot represents the trend of the relationship between the two variables rather than joining the dots together as with a line graph. The regression line can be used in some circumstances as a productive tool. For example, my scatter graph shows the relationship between an individual's chest throw and their vertical jump. With this graph, I can potentially be able to predict that if someone has a vertical jump of 40 centimeters, they will have a chest throw of around 780 centimeters. Next is line and SD bars. Standard deviation simply calculates and shows the spread of data around the mean and is used when data distribution is normal and not skewed. If data points are close to the mean, this means there is a low standard deviation. If data points are far from the mean, this means there is a high standard deviation. It is also used to see whether a specific data point is standard and expected, or if it is unusual and unexpected. 68% of data lies within one standard deviation either side of the mean, 95% lies within two standard deviations either side of the mean, and 99% lies within three standard deviations either side of the mean, as shown by one of the images. SD error bars are used to show variability in data by showing the reliability of the mean value as a representative number for the dataset and the likelihood of there being a significant difference between the datasets. When standard deviation error bars overlap quite a bit, it is a clue that the difference is not statistically significant. When standard deviation error bars do not overlap, it is a clue that difference may be significant. You must perform a statistical test, however, to draw a conclusion. Next is box plot and whiskers. Box plot are used to show the shape of the distribution, its central value and its variability. In a box and whisker plot, the ends of the box are the upper and lower quartiles, so the box spans the interquartile range. The box plot shows the minimum value of the resting heart rate as 55 and the maximum as 92. The first quartile is around 65, the median, also known as the second quartile, is around 72, and the third quartile is around 74. The box plot also shows the dispersion of the data around the median, as there are the same data value either side of the median, but the first quartile has a wider dispersion of data due to the box of the first quartile being bigger than the box of the third quartile. Using a box plot, you can also calculate the interquartile range by subtracting the first quartile from the third quartile. Next is histograms. A histogram is only used to plot the frequency of score occurrences in a continuous data set with no gaps between the bars, unlike a bar chart. They show an underlying frequency distribution of continuous data set. This allows us to see outliers and skewness on data sets. In one example, if the men's data set shows a high standard deviation as the data points are more dispersed from the mean than women's, the mean being the highest peak on the graph. That's what the image on the right shows. Next is distribution curves. A normal distribution curve shows a bell curve if data is normally spread out and evenly, and shows the dispersion of the data around the mean. If the distribution curve is tall and narrow, the data variation is close to the mean. If the distribution curve is flat and wide, then the data variation is more spread out or more dispersed either side of the mean. Depending on whether data is approximately normally distributed or not, we can pick a statistical test. If data is normally distributed, we can use a parametric test. If data is not normally distributed, then we can use a non-parametric test. And that's the data statistical selection there. If data is normally distributed, you use a parametric test. If it's not normally distributed, you use a non-parametric test. Next is skewed data sets and outliers. Outliers are data points that appear significantly different to the rest of the data set. However, even if a data set looks significantly different, it's not enough for us to just say that it is an outlier and be subjective about it. We must perform a statistical test. The way to statistically determine an outlier is by finding the first quartile, median and third quartile. You can then calculate the interquartile range, and you multiply the interquartile range by a number which varies depending on what source you credit. In this case, I will multiply my interquartile range by 2.2. Then whatever the number you calculate, you plus that number to the third quartile, and any number that is above this number is an outlier, or you can minus the number to the first quartile, and any number that's below this is an outlier. Here you have inferential stats. Adding on the slide before, with my box plot example, my first quartile is 65 and my third quartile is 74. So my interquartile range would be 74 minus 65, which equals 9. Then multiply 9 by 2.2, as this is the variation I chose. This equals 19.8. I would then add 19.8 to my third quartile, which equals 93.8. And any number that is above 93.8 is an outlier. I would do the same for the first quartile by subtracting 19.8 to the first quartile, which is 65. So 65 subtracted 19.8, which gives you 45.2, and any number that is below 45.2 is an outlier. Next is skewed data. Negatively skewed data shows that most of the data on the graph at the higher number value on the x-axis, and positively skewed data shows that most of the data is at a lower number value on the x-axis. So next is the inferential stats. Most research will look at statistical significance of the conclusion of your findings. It is not enough to simply say that data and findings are rather significant without performing a statistical test. The significance of the final concluded data of an experiment is by using the p-value, which will be 0.05. If the calculated result is below 0.05, then the results are statistically significant. If the data is 0.05 or above it, then results are not statistically significant. However, the researcher should still not ignore the practical significance, as this could be a change in the dependent variable showing a potential difference between the data sets that could be potentially significant, that shows a relationship between the two sets of the data but not mathematically significant. For example, if the independent variable is caffeine and you test whether it has an effect on vertical jump being the dependent variable, you measure the effects of caffeine on the vertical jump of some female British gymnasts before caffeine, pre-test, give them caffeine, and then measure again in a post-test. if their vertical jump increased, the increase in vertical jumps after they took caffeine could be potentially practically significant, but not mathematically significant if calculated. In the first stage that the researcher will do when they receive their concluded data results after an experiment is that they will look to see if there's a difference in the means of the two data sets. If means are different, the researcher can use practical significance to make an assumption of if the mean is big enough to be significant, but they're not sure whether this is a reoccurring difference or whether it could be due to luck. The second stage is for them to try and see whether the results of the data they received are mathematically significant in order for their results to be deemed credible by other researchers. This can be done by stating a null hypothesis, then doing inferential statistics. A null hypothesis is stating that there will be no significant effect or outcome of results obtained from the pre-testing and post-testing. This means the researcher needs to evidence that the null hypothesis is wrong by doing an inferential test that shows his calculated t-value being lower than 0.05, so it is significant and therefore can reject the null hypothesis. The alternate hypothesis suggests that there will be an outcome or an effect on the different data value. This means if the calculated t-value is below 0.05 and therefore significant, the alternate hypothesis can be accepted. When using the alternate hypothesis, there are two sub-hypotheses underneath it. This is the non-directional hypothesis and the directional hypothesis. The non-directional hypothesis is the researcher stating that there is an outcome/effect, but they don't say whether it is going to be positive outcome, as in results get better, or a negative outcome, as in results get worse due to whatever they're experimenting on. This means it is two-tail. The directional hypothesis approach is stating that there will be an effect/outcome, and the researcher also states whether it will be a positive or negative effect on the results, and this means it is one-tail. When using inferential stats, we compare the significance of the data received at the end of the experiment and compare it to the p-value, which is 0.05. However, the other researchers might use different p-values depending on how accurate they want their conclusion of the significance of their data to be. If the calculated t-value given from the data is that they collected is below 0.05, then the result is statistically significant. If it's 0.05 or above, then it is not statistically significant. So this image right here shows you how for test selection. So you start where it says start, and then you base it on whether you're looking for a difference or correlation or category in the test. And so let's say you're looking for a difference, as we are. You base it upon how many factors you're doing. So if, let's say, you were doing the effects of caffeine on vertical jumps of young female British gymnasts, and that's only using one factor, which is the caffeine as the intervention. So you go down the route of the one factor, and then if you're doing that on the same participants or subjects, so the same group of people, you test them before and then give them caffeine and then test them after. So that's the same participants, and then you go down the same route, and then you depending on whether your data is parametric or non-parametric, which is where it's normally distributed. If data is not normally distributed, then you use a non-parametric test, and if it's normally distributed, you can use a parametric test. So here it shows you the independent t-test. We had participants of 10, and then we had a flying start of group A and then flying start of group B. So then we calculate the mean of the first group and then the mean of the second group. Then we calculate standard deviations of both the groups. And on the right shows you the image of the calculations that we've done to get our t-value as 6.017. And then to get the degrees of freedom, that equals n1 plus n2 minus 2, which gives you degrees of freedom of 18. And then you go down to 0.05, as that's the level of significance we're using in the two-tail test, and it will give you a critical value of 2.017. 101